Okay, can I have the first slide? So today in my talk, I chose of the many topics possible just to talk as the first speaker about the foundations and about the fundamental questions, the fundamental concepts, and maybe I'm allowed to also put down here some speculative ideas of what we are talking about. Here we go. Now, next year we celebrate, as it was already mentioned by Bill, 100 years of the theory of quantum mechanics, with Heisenberg 1925 publishing his matrix mechanics. And Heisenberg is known broadly for his uncertainty relation, namely that the position and the momentum of a particle cannot be known precisely, but there is a limit. And Heisenberg himself says, and this is already the first important message, the uncertainty is not about I don't know, it is I can't know. I am uncertain does not mean I could be certain, because this is a fundamental undefinedness of nature. In the same year, published 1926, Erwin Schrödinger, I think Heisenberg and Schrödinger were both members of this academy, if I understand it correctly, published his wave mechanics. Here is a wave equation written by Schrödinger himself out of one of his notebooks. And this equation is opened up a lot of research on laser indirectly, that was earlier by Einstein, semiconductors, computers. Schrödinger himself said, my equation makes chemistry a part of physics. And that's actually an interesting program to fulfill this in every detail. But the point was the interpretation from the beginning on. What do these symbols, which you see here, I don't want to go into details, mean? And there are two levels of interpretation. I claim at least two levels of interpretation in any physical theory. One is to explain what the symbols mean in terms of going into the laboratory and doing experiments. On that level, there is nearly no disagreement in quantum mechanics. The second level is another one. What does this new physics mean for my understanding of the world? For what we call Weltanschauung in German, and there things are wide open. Here you see below also the equation written down in the shortest possible way on the grave of Schrödinger in Alpbach in Tirol. So you ever come to Tirol, visit it. Now, a first way to discuss things is the so-called double-slit interference phenomenon. Here's a drawing out of an article written by Niels Bohr about his discussions about the double slit. The point is, if you have from the left, for example, light incident or anything else, it doesn't matter. If both slits are open, as shown here, then you get stripes, observation stripes, which can be understood as interference, as wave phenomenon. But if you close this one slit, or if you know which slit the particle passed through, there are no stripes. So we are talking about path information versus interference, particle information versus wave information. And these two are called complementary. This is an example of complementarity. You either can know one or the other. The debate between Einstein and Bohr was about, in a nutshell, Einstein claimed that physics has to describe what is really out there in every detail. So physics should contain information about the path and the interference pattern and all this. And Bohr said, that physics can only be about what can be said about nature. That's a very important difference to which I will come back a little later. When we talk about the double-slit experiment, the old view, the traditional view, is that information, that the interference disappears as soon as you disturb the path of the particle along the two slits. The modern view is that that the two informations, the one information which is contained in the path identity and the other one in the wave are limited. The total information is limited. And there can only be one of the two well-defined or a combination of two, but never each one perfectly. Now here's an experiment. I'm an experimentalist. This is an experiment we did in 1988. That's the pattern obtained with neutrons, just these stripes I mentioned in my talk. And one of the co-authors was Giff Schall, who received the Nobel Prize in 1994 for neutron diffraction. And what's important about this pattern, the observed distribution, is number one, the solid line is theory without any free parameter. So that actually confirms an important feature of quantum mechanics, namely the linearity of the Schrödinger equation. And the second point is that even at the highest intensities, you cannot read the numbers here. The neutrons were collected one by one. When one neutron was detected, the other neutron, they come out of a nuclear reactor in the core of the nuclear reactor. The other neutron was still sitting in its uranium nucleus, waiting for fission to set it free. And that's a completely random process, by the way. Now, so this is one by one. And when this is something expected, but when I gave those talks very early as a young chap, even famous people in the first row came up and said, it really works that way, one by one particle by one. So each particle has to have information that both slits are open. Because it wouldn't have that information, you would not get the interference pattern. Let's go on. Now, the question is, how far can we go with these interferences? They have been done with electrons, neutrons, atoms, small molecules. The question is, they are limited in size. And that's a research program going on in various laboratories. Very early, we did experiments with these buckyball molecules. And my viewpoint is that there is no limit. There is no limit in mass, there is no limit in complexity, no limit in temperature. It just depends on the cleverness of the experimentalist, on experience over the time, and lots of money. Now I want to tell you a strange experiment here. A strange experiment where you have here a laser which produces laser light which passes through a crystal. And that crystal produces pairs of photons, and in one of the two pairs, you put the double slit to see the interference. And on the other side, you can use detectors at different positions, which would allow you to determine the path the other particle passed through, because that detection is done much later than the other one, or it would allow you to see a distribution which corresponds to the interference pattern. So to the lower left here, to the left is the double slit pattern, to the right is the distribution without interference. So the beam splitter decision can be made randomly if you want with some special devices. So your decision, what to measure on the other particle, defines whether the one you registered already passed through one well-defined slit or shows the interference pattern. Now, this signifies, and that actually is a nice confirmation of the famous saying by Bohr, no phenomenon is a phenomenon unless it is an observed phenomenon. So you shouldn't assign properties without the experiment actually done. All this is due to, and that's the second concept I want to bring you today, is due to entanglement. Here's a famous paper by Einstein in 1935 with the philosophical title, Can Quantum Mechanical Description of Reality Be Considered Complete? And that paper was actually never seen by a referee. And as soon as Physical Review sent his papers to referees, he did not send them anything anymore. He says, I don't see why my paper shouldn't be immediately known by everybody. Okay, very interesting. Now, in this situation, Einstein says, together with Podolsky and Rosen, that two objects, two particles, is there a laser pointer actually? No, it's not here. Shown here, which interacted in the past, have a state which is not separable. So each of them does not enjoy a well-defined state. They are not, when we measure them, they are completely random, but the two are perfectly correlated. This was called by Schrödinger in the same year, Verschränkung in German, entanglement in English, and he said, I would not call that, namely entanglement, one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. And Schrödinger writes very nicely already that only joint expectation catalogs for the two particles exist and no expectation catalogs for individual systems. In modern language, you can substitute expectation catalog by information. This was actually a very deep point of view of Einstein, of Schrödinger. Now, the whole discussion about whether entanglement exists and all this was long considered to be just philosophical. Then came John Bell, Irish physicist, in 1964, and he showed that if you have correlations between two particles, here the polarization, then if you look at the correlations explainable by any local realistic model. Local meaning what I do here does not depend what happens at the same time at some distant location. And realistic means that the experimental results are given already prior to and independent of my observation. This model gives correlations which are weaker than what quantum mechanics predicts. And there's a long story that about experimental verification of that situation. Here is an example, more recent, where we showed that this kind of entanglement exists over a distance of 144 kilometers between two Canary Islands, which laid the ground for long-distance quantum communication, which I don't want to mention today. Here's an experiment where we actually used light from quasars, very, very distant objects, to trigger which measurement is performed, because we wanted to have two completely independent decisions for the two measurements. No hidden cause. To me, conceptually still mind-boggling case is what's called entanglement swapping. I just want to explain it very briefly. You have two sources down there, with each one produces an entangled pair. Remember, entangled means that neither of them has well-defined properties, but only jointly. And then you measure one of the photons from each, and you record the results. And the other two photons, you decide at a later time, when these were already recorded, whether you measure their features, their state individually or jointly, whether you project, as we say, the state onto an entangled state, in which case the outer two records already registered confirm that these photons were entangled. Or you measure them separately, in which case the outer two results confirm that they were not entangled. and not entangled with each other, but just with its neighbor. To me, this is the most beautiful, it is an idea by Asher Perez from 2001, the most beautiful manifestation that all this is about. Sorry? 2 minutes? 5 left, including discussion or without? Okay, no. Okay. Okay, I come to my final statements. Maybe we can skip this. I said a famous statement by Bohr who says that there is no quantum world. There's only an abstract quantum physical description. It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. From that point of view, one can claim of the universe. I pass this one. It's information about measurement results which allow you to make predictions for future measurement results. So it's all about classical information, properties of the apparatus. I come to the end here. I've often asked myself, why do we have quantum physics, besides its fantastic agreement with experiments? Okay? And I would suggest here that what we need an analysis of what it means to use information. We need a Gödel-type analysis of logical statements in quantum physics. This has to include also the limits to information which lead to quantum uncertainty. And I suggest maybe information is the most basic concept, Urstoff, of the universe. And this has already been said. The Gospel according to John begins with, in principio erat verbum. Thank you very much for your attention.